Okay, chapter 1, section 2, exponents and radicals. So in this section, we're going to cover integer exponents. We're going to cover rules for working with exponents, scientific notation, radicals, rational exponents, rationalizing, denominators, standard form. Okay, integer exponents. A product of identical numbers is usually written in exponential notation, right? So hopefully this looks familiar. Here, highlighter, let's go here. So if we have a multiplication of 5 times 5 times 5, something like this, 5 times 5 times 5, we can express this by writing it in this form, right? 5 to the power of 3. 5 to the power of 3 means we multiply that same base value 5 times itself 3 times, right? So in general, if a is any real number and n is a positive integer, for now we're just going to stick to positive integers, then the nth power of a is a to the nth power, which means that we multiply a times a times a times a, n a's being multiplied, and that's what this notation means, right? So likewise, then 7 to the power of 4 would then be 7 times 7 times 7 times 7, 1, 2, 3, 4, for example, right? Other examples. There's a couple of other examples. What if we had 1/2 to the power of 5? Well, then this would then be 1/2 times 1/2 times 1/2 times 1/2 times 1/2. 1, 2, 3, 4, 5 of them being multiplied. And then, of course, we know from multiplication of fractions that this is equivalent to 1 over 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5 of them, which is the same thing as 1 over 2 to the power of 5. And then 1 over 2 to the power of 5 is equal to 1 over 32. Right? 2 times 2 is 4, then 8, then 16, then 32. 1 over 32. Okay. Okay, here's another example. Now, this one we have to be careful about because these two get confused very, very often, okay? So this one, notice that it's the negative 3 is sort of wrapped around parentheses to the power of 4, whereas this one is not. So when we're dealing with this, negative 3 to the power of 4 in parentheses like this one means that we're going to have negative 3 times negative 3 times negative 3 times negative 3, 1, 2, 3, 4 times. And now a negative times a negative equals a positive. So I know these two are going to give me a positive 9. Negative times a negative equals a positive. So I know that these two are going to give me also a positive 9. And so my final answer is positive 81. Right? We can also just keep track of how many negatives there are. There's 1, 2, 3, 4 different negative signs. So that's how I know that the final answer is going to be positive. Right? Now, on the other hand, this guy doesn't have parentheses around the negative. Negative 3 to the power of 4 without parentheses. This one really means that we have a negative 1 times 3 to the power of positive 4. Right? So, in other words, the 4 in the exponent does not apply to the negative. It only applies to the 3. If you wanted it to apply to the negative, well, that's what the parentheses are for. Okay, so then if we expand this, we'll have negative 1 times times 3 times 3 times 3 times 3, 1, 2, 3, 4 of them. And so once we multiply that all out, we end up with negative 81. Right, so the answer to this one equals to negative 81. Put it in color here. The answer to this one is negative 81. whereas the answer to this one is positive 81, right? So that's why they're different. Let's try a couple more. We can also get stuff that's a little bit more interesting. Like, for example, we could have something like a plus b to the power of 3, right? This, what this means is that we're going to repeat this, multiply by itself 3 different times. So this is a plus b, a plus b, a plus b, right? So right now all I'm pointing out is what this little value up here means. And for the moment, we're only considering the case where it's a positive counting number. Good? Okay, so let's move on. Rules for working with exponents, right? So what are the rules for working with exponents? So we're going to have several rules. So let's see. Rule number one, we're going to say that x to the power of m times x to the power of n is equal to x to the power of m plus n, right? So when we have two exponential numbers being multiplied and they have the same base, then all we have to do is add the exponents. That's the first rule. So for example, if we had 3 to the power of 7, well, let's make it 2. 3 to the power of 2 times 3 to the power of 4. Okay, this means that we multiply 3 by itself twice, so that's going to be 3 times 3, that's what this one means, times, now this one means we multiply 3 by itself 4 times, so we're going to have 3, 3, 3, 3, 4 of them, and then if we count them all, now we have 6 of them, 1, 2, 3, 4, 5, 6, right? 2 of them came from this, 2 of them came from here, while the rest, the other 4, came from over here. But at the end of the day, no matter where they came from, we're looking at 1, 2, 3, 4, 5, 6 of them being multiplied. So this equals to 3 to the power of 6. Right? So if we look at the original question and what the final answer is, then we could see that the shortcut is that when we have two exponential numbers being multiplied with the same base, then all we have to do is add the exponents. 3 to the power of 2 plus 4, which equals to 3 to the power of 6. Good? Okay, so keep that in mind. When they're really easy numbers like this, hopefully it's clear. But then when we run into something a little bit more complicated, you just have to rely on this working out, right? So if we were only dealing with variables, like for example, it could just be a to the power of 4 times a to the power of 3. Well, we know this must be equal to a to the power of 4 plus 3, which then equals to a to the power of 7. Or if we had something even more complicated, we could have something like a plus b to the power of 2 times a plus b to the power of 7. Right. So now here again we have something being raised to the power of 2, something being raised to the power of 7. These two things are identical. So this is an exponential times another exponential. This is equivalent to a plus b to the power of 2 plus 7, which then equals to a plus b to the power of 9. Good? Okay, so that's the first rule. This one, two exponential numbers with the same base, we add the exponent. All right, rule number 2. Rule number 2 is that x to the power of m divided by x to the power of n is equal to x to the power of m minus n. All right, let's look at an example to see how this is true. So for example, if we had 3 to the power of 5 divided by 3 to the power of 3, okay, if we expand them out, the numerator would mean that we multiply the 3 by itself 5 times. So in the numerator, we should have 3, 3, 3, 3, 3, 1, 2, 3, 4, 5 of them, divided by, in the denominator, we have 3 to the power of 3. So that should be 1, 2, 3 of them. And we know from reduction in fractions that means that these two form a 1, they cancel. These two form another 1, 3 over 3 is 1, right? 3 over 3 equals 1, so they reduce. And then 3 over 3, they reduce. So we know that after reduction, this just equals to 3 times 3, which is equal to 3 to the power of 2. And again, if we want to look at our shortcuts, right, if we want to establish a shortcut, we can see that the starting statement, go back to where we started, this one, if we take the base 3 and then we subtract them in the following order, it's got to be this exponent minus this exponent, right? So it'll be 5 minus 3. 5 minus 3. So that'll be 3 to the power of 2. Right? So we get the same answer. Right? The shortcut works. Good, good, good. Okay, so we want to rely on this formula, rely on this shortcut, even if they get a little bit more complicated. We could have something like b plus 2 to the power of 7 divided by b plus 2 to the power of 4. Right? And again, these two are identical. This is an exponential number raised to the power of 7, another exponential raised to the power of 4. They're identical. So relying on my rule, that must mean that this is b plus 2 to the power of 7 minus 4. It has to be in this order, right? So this will be b plus 2 to the power of 3. Good. So remember the order. It's got to be the exponent with the exponential number that's in the numerator, the exponent of that exponential number, it goes first, minus, let's put it in, see if this one looks a little better, minus this one, the exponential number in the denominator. And that's how we get this. Good, so that's our second rule, rule number 2. All right, moving on, rule number 3. There'll be a little table in a second that brings all these together. Rule number 3, x to the power of m raised to the power of n is equal to x to the power of m times n, right? Often we don't put that little indication, that little dot to indicate multiplication, so this would just be x to the power of mn, right? Okay, don't confuse this with rule number 1. Let's look at an example. So if we had 3 to the power of 2, and then that whole thing is being raised to the power of 4, okay? All right, well, let's peel this like an onion from the outside in. This 4 out here means that we're going to repeat this, right? It applies to the whole thing. This whole thing gets repeated 4 times. So this would mean that we have 3 to the power of 2 times 3 to the power of 2 times 3 to the power of 2 times 3 to the power of 2. All right, 1, 2, 3, 4 times. Good. These parentheses are there to just simply indicate that we have this quantity multiplied by this quantity multiplied by that quantity, right? So they're not really necessary in this context, so I can just get rid of them. This is 3 squared times 3 squared times 3 squared times 3 squared. Okay, well, we have exponential numbers being multiplied with the same base, so we learned from before that all we have to do is add the exponents, right? if you don't remember that, then we can again further break this down and say that each one of these means we multiply a 3 times a 3, and a 3 times a 3 from there, and another 3 times a 3 from there, and then another 3 times a 3 from that last one. So any way you slice it, we end up with 1, 2, 3, 4, 5, 6, 7, 8 different factors of 3. So this is the same thing as 3, right? We can kind of skip this step. We can skip this step and go to this step and say that this is equal to 3 to the power of 2 plus 2 plus 2 plus 2 using rule number 1, right? We add the exponents whenever we're multiplying exponential numbers. And so any way you slice it, we end up with 3 to the power of 8. 3 to the power of 8. Okay, and so now we start to see what the rule is then. So 3 to the power of 2 raised to the power of 4 is equal to 3 to the power of 2 times 4, which equals to 3 to the power of 8. Right? So that's how we get the same answer. That's our shortcut. Do not confuse this with the other one, right? So this is rule number 3. Rule number 2 gets confused very often, right? So let's note that it's different. If we had 3 to the second power times 3 to the fourth power, this would be a case of rule 1. 2 exponential numbers being multiplied with the same base. Rule number 1 says, what do? We add the exponents. This is 3 to the power of 2 plus 4, which gives me 3 to the power of 6, right? That's different from here. 3 to the power of 2, that whole thing being raised to the power of 4, right? So it's an exponential number being raised to another power. That's different than 2 exponential numbers being multiplied with the same base. In this case, we add the exponents, so we get a 6. And in this case, we multiply the exponents. Therefore, we get an 8. Okay, let's move on then. The next rule, rule number 4. Rule number 4. Rule number 4 then is this one, very similar. If we had a, b raised to the power of n, we have ab raised to the power of n, this is equal to a to the nth power times b to the nth power. There's sort of a distribution of exponents that happens here. So let's look at an example of why that is. So for example, if we had 2x raised to the power of 3, right? This 3 means that we repeat this, we multiply this by itself 3 times. So that would be 2x times 2x times 2x, which means that I can regroup these, right? These parentheses are just indicating that this quantity is being multiplied by that quantity, so I can get rid of them and say that this is just 2x, 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 everything's being multiplied. So I can reorder them and put all the 2's together, and then put all the x's together. And then I can rearrange them and say that this can be written as 2 to the third power, and this can be written as x to the third power. And if we compare it to the original statement, we have 2x raised to the power of 3. Well, that's just going to be 2 to the third power, x to the third power. Good. Okay, so then let's do another more complicated example. Notice that this has to be multiplication, though. Let's say we had 8x to the fourth power, and all of that is being squared. Okay, so doing it the long way, I'm going to go ahead and break this down and say that this is equal to 2 to the third power, that's what an 8 is, x to the fourth power, the whole thing being squared. And now the squared means we'll repeat this twice, so that would be 2 to the third power, x to the fourth, times 2 to the third power, x to the fourth, right? Okay, so then we can regroup them, and we end up with 2 to the third power times 2 to the third power x to the fourth power, x to the fourth power. And then we can group these up using rule number 1. This is 2 to the power of 3 plus 3. This is x to the power of 4 plus 4. So this is going to be 2 to the power of 6 times x to the power of 8. Good? Okay, so we're fairly convinced that's the right answer. So now let's come over here and do it using this little shortcut property. We have that. Well, the first thing I'm going to do is just rewrite the 8 as 2 to the power of 3 times x to the power of 4, all of it being raised to the power of 2. Okay, so there's this little distribution property that happens. This is going to be equal to raising this to the power of 2 and then raising this to the power of 2. This will be 2 to the third power squared times x to the fourth power squared, which then gives me, using the previous rule, rule number 3 I think it was, that this is going to be equal to 2 to the 3 times 2 times x to the 4 times 2. So we end up with 2 to the 6th power times x to the 8th power. Okay, all right, so that's, again, this rule right here, rule number 4. Okay, rule number 5, very similar. Rule number 5, if we have an a over a b and the whole thing is being raised to an n, then we can again do this sort of distribution and say that this is a to the nth power divided by b to the nth power. So for example, if we had 3 over x and the whole thing is being raised to the power of 4, then this 4 is saying that we repeat this 4 times, so there would be 3 over x times 3 over x times 3 over x times 3 over x. 1, 2, 3, 4 different times. And so we know that that must mean that this is 3 to the power of 4 divided by x to the power of 4. Okay, and that's what that little shortcut is telling us, right? That we don't have to do this middle step, we can go from there to there. So if we have a more complicated situation, like let's say we had 2ab squared divided by 3w to the third power, and the whole thing is being raised to the power of 5. Right, so we can combine some of these tricks now. So the first one is to say that this fraction, right, we can separate it and raise the numerator to the power of 5, raise the denominator to the power of 5. So this would be 2ab squared, and the whole thing being raised to the power of 5, divided by, and then in the denominator we have 3w to the third power raised to the power of 5. Good. Okay, and now we can use some of the other properties we learned, some of the other rules. So we get to kind of do this distribution of exponents. And so we'll end up with, in the numerator, we'll end up with 2 to the power of 5, a to the power of 5, and then b squared gets raised to the power of 5. In the denominator, we'll get 3 to the power of 5, and then the w cubed also gets raised to the power of 5. Okay, so finally we can reduce this. This will end up with 2 to the power of 5, a to the power of 5, and then b squared raised to the power of 5. We know that that must mean that we multiply the exponents. And then we'll end up with a 3 to the power of 5 there, and a w to the power of 3 times 5. Good. For a final answer of 2 to the power of 5, a to the power of 5, b to the power of 10, divided by 3 to the power of 5, and w to the power of 15. Good. That's as good as it goes. Now, there's a question about these. Should we leave them like this, or do we actually multiply them out and expand them and write them out? Well, that's kind of hard to say. Personally, I accept either one. In fact, I like exponential number notation better, so I would stop there. But when you go look, for solutions in the back of the book, are they going to write it this way, or are they going to expand it? Well, the general guideline, the general rule of thumb here is that if the multiplication happens to be less than 1,000, if the answer is less than 1,000, then they do expect you to write it out. And if it's bigger than 1,000, then they usually just leave it in exponential notation. So 2 to the power of 5, that's going to be 32. So 2 to the power of 5 is 32 times a to the 5th, b to the 10th, over, and 3 to the 5th power, I think that's 243. Okay, so that's our final answer. Like I said, I would be happy with this one, but the general guideline is that if this exponential, if you multiply it out and the answer is less than 1,000, they expect you to actually multiply it out. And if it's more than 1,000, then they would leave it alone like that. Okay, hopefully that's a good example. Let's move on. This was rule number 5. Okay, so let's get on to the following idea then. So keeping in mind that from rule 2, we know that if we have 3 to the power of 5 divided by 3 to the power of 2, we know that there's going to be 5 copies of 3 in the numerator, 2 copies of 3 in the denominator. A bunch of those will reduce. We know from our second rule that this is equivalent to 3 to the power of 5 minus 2, which is equal to 3 to the power of 3. Good. Okay, so keeping that rule in mind, think about what happens when we have something like this. 3 to the power of 5 divided by 3 to the power of 5. Okay, if we ignore the rule for a second, we can just expand out the 3's. That's 3, 3, 3, 3, 3, 1, 2, 3, 4, 5 of them. And then in the denominator, we're going to have 1, 2, 3, 4, 5 of them again. And then they all cancel, right? 3 over 3, 3 over 3, 3 over 3. They're all different forms of 1. So I know this must be equal to 1. Well, you didn't even have to do this step here. We know that whenever we have a fraction and the numerator and denominator are identical, they cancel, they reduce, and give you a 1, right? So we're convinced that this has to be equal to 1. But at the same time, we want this little rule to work, right? The little rule said that if we have a fraction where we're dividing an exponential number by another exponential number, and they have the same base, then we subtract the exponents, right? The power in the exponential number in the numerator minus this one, right? The power in the exponential number in the denominator, in this order. We want that rule to hold true. But if we apply that rule here, right, we have 3 to the power of 5 divided by 3 to the power of 5, and we apply that rule, we'll end up with 3 to the power of 5 minus 5, right? Where I'm getting this guy here is this one, and this denominator one is this one, and so this just equals to 3 to the power of 0. Okay, well, we fix it. How do we fix it? We just make sure that we define these two things to be equal. Define to be equal, right? So 3 to the power 0 must be 1, right? Because we want this whole rule to work out. This must be equal to that. Good. Well, it turns out that that's true for any number. 3 was just an arbitrary value. We could do the same thing with any other number. So, for example, if I had 7 to the power of 11 all over 7 to the power of 11, well, that's the same thing. 7 to the 11 minus 11 What's 7 to the 0 power? Well, that's got to be a 1. Right? So one of the rules, the next rule, is that any number a, for any real number a to the 0 power is always 1. For any real number a. Good. Okay, and while keeping in the same spirit of figuring out or keeping that rule in mind, what if we had 3 to the power of 2 divided by 3 to the power of 5? Okay, so that means that if we expand the numerator, that would be a 3 and a 3 up there, divided by, now in the denominator, we'll have 1, 2, 3, 4, 5 of them. And so now a few of them will cancel. This will reduce with that, this will reduce with that, and now we'll have 3 factors surviving, but they'll be in the denominator. So this is going to be 1 over 1, 2, 3, which is equal to 1 over 3 to the power of 3. Okay, but what about my rule? Let's keep our rule in mind. That was 3 to the 2nd power over 3 to the 5th power. And remember, I've made a big deal that the order matters, so this has to be 3 to the power of, it's got to be this one minus this one minus this one. Good? So this will be 2 minus 5, 2 minus 5, where this is the one from there. It's always the power of the exponential number in the numerator of the fraction minus the power of the exponential number in the denominator in this order. But now what's going to happen when I subtract them in this order, I'm going to get a negative number. This is going to be equal to 3 to the power of negative 3. And again, how do we reconcile these two things? Easy, we fix it. We make them equal to each other. Equal. Okay, so the moral of the story here is that if we have a negative in the exponent like this, then it's equivalent to 1 over the exponential number, and then we change this to a positive. Right? That's what that's saying. So, there's nothing special about the number 3. That's just an arbitrary value. So if I chose 8 to the power of negative 5, I can get rid of that negative, according to this little rule here, by rewriting it as 1 over 8 to the power of positive 5. Right? And that's our next rule. So where was I with these rules? Rule number 5. So rule number 6 is this one. This one was rule 6. Rule number 6 is this one. That a to the 0 power equals to 1 for any real number a. And rule number 7, whoa, I have space here. Rule number 7 is that a, the power of negative n, is equal to 1 over a to the power of n. Good. And that's for any real number a. For a equal to any real number. And we have to keep in mind that a is not allowed to be 0, though. Then we'd end up with something weird, right? And a does not equal 0. Good. Okay, just a couple more rules that kind of combine the stuff we've already been doing, so hopefully they're not too bad. We'll say rule number 8, and then we'll run into a nice table in a second. So if we had a fraction a over b raised to the power of negative n, the rule is that this is equivalent to b over a raised to the power of positive n. Right? So this minus in the exponent here can be used to flip this around. Right? So let's see an example of why that is. So let's say, for example, I had 3 over x raised to the negative 4 power. Well, we already know from a previous rule that this must mean that I can raise 3 to the power of negative 4, divided by x to the power of negative 4. And we just figured out that in order to get rid of that minus in the exponent, this is equal to 1 over 3 to the power of positive 4 divided by 1 over x to the power of positive 4. Right? That's how we get rid of that negative. And then how do we simplify this? We have a giant fraction where the numerator is a fraction, the denominator is a fraction. Remember, we keep, change, flip. So we keep the exponent alone, and then we multiply it instead of divide it times the reciprocal of the denominator, and the reciprocal would then be x to the 4th power divided by 1, which then multiplies to x to the 4th power divided by 3 to the 4th power. And then as a final touch here, we can say that this is equal to x over 3 to the power of 4. Right? So if we look at where we started from, let's focus back over here, the original statement. After all these steps here, we end up with this one. And that proves the rule. Right? All we did was get rid of this little minus in here. The exponent had a minus. At the end of the day here, we don't have a minus. It's a positive 4 instead of a negative 4. And then we had a 3 over x, so then we just flip this guy around. Right, so that's what this shortcut here is indicating for us. And finally, the last rule we're going to look at, rule number 9. Rule number 9 is that a to the negative nth power divided by a to the negative m power is equal to, whoops, let me restate that. To the negative n power divided by b to the negative m power is equal to b to the positive m power divided by a to the positive n power. Good. And again, let's illustrate that with an example. If we had 3 to the power of negative, negative 7 divided by 2 to the power of negative 5, well, we just stated that to get rid of that minus there, we know that all we have to do is flip it underneath 1. So that would be 1 over 3 to the positive 7th power in the exponent divided by, and to eliminate that little minus there, this becomes 1 over 2 to the 5th power, like that. And then we multiply the numerator times the reciprocal of the denominator. So that would be 1 over 3 to the 7th power times 2 to the 5th power divided by 1, which gives you 2 to the 5th power divided by 3 to the 7th power. Good. So we see if we compare where we started to where we ended. This is where we started compared to where we ended. We take the exponential number that has a negative in the exponent, right? We end up with it in the denominator with a positive in the exponent. And that's what's happening here. We have some exponential number with a negative in the exponent. We move it down to the denominator and make it a positive one. And then for this one, we started off with an exponential number with a negative in the exponent here, and we end up with it up in the numerator with a positive exponent. Right? We started with 2 to the negative 5 there. It ends up with 2 to the positive 5 there. Okay, so this is the reason why that's true. Hopefully that makes sense. But there's a nice little shortcut here that we get to use. And the way we normally kind of utilize this shortcut is just to say we, quote-unquote, move the exponential number from the numerator to the denominator or from the denominator to the numerator and change the signs. Right? So, for example, we could have a more complicated statement like 3 to the negative 8, x to the positive 4 power, y to the negative 2 power, all over 2 to the negative 5 power, w to the negative 6 power, and q to the positive 3 power. Say we have a really complicated thing like this, and we wanted to simplify it. Well, let's do it the long way, and then we'll look at the really easy little shortcut. So if we're going to do it the longer way, we have to take care of all these negatives in the exponents. So we'll end up with a bunch of fractions. We'll end up with 1 over 3 to the positive 8th power times x to the 4th power times 1 over y to the positive 2 power. That takes care of the numerator. In the denominator, I'll end up with 1 over 2 to the positive 5th power, 1 over w to the positive 6th power, and then q to the 3rd power. Right, we can always put a over 1 to turn it into any whole number into a fraction, so we can always put that there. And so now we have a multiplication of these guys in the numerator. We don't need a common denominator or anything, so multiply across the numerators, multiply across the denominators. So we end up with one big happy fraction that has an x to the 4th power, a 3 to the 8th power, and a y to the 2nd power up in the numerator. So we have that ugly fraction there. And in the denominator, we do the same thing. We'll end up with a q to the 3rd power divided by 2 to the 5th power and a w to the 6th power, like that. Okay, so now we have one big ugly fraction where the numerator is a fraction, the denominator is a fraction. So the way we simplify this is to multiply the numerator. Well, let's put it over here actually. So we're going to multiply the numerator, which is x to the 4th power divided by 3 to the 8th power, y to the 2nd power, like this. And we're going to multiply it times the reciprocal of the denominator, which is a 2 to the 5th power times a w to the 6th power divided by q to the 3rd power. Good. Which then equals 2. Well, okay, well now we just multiply across, so we'll end up with 2 to the 5th power times x to the 4th power, w to the 6th power, all over 3 to the 8th power, w to the 2nd power, and q to the 3rd power. Okay, so that's our final answer. What we want to do is look at the pattern, right? Again, think about where we started and where we ended. And this is the reason why it's true, so hopefully it makes sense. But let's just look at these individual things. So x to the 4th power had a positive exponent, and it was in the numerator to begin with, and that's where it ended up. It's in the exponent, it's in the numerator, and it's exactly the same thing. Same thing with q to the 3rd power. It already had a positive exponent, right? Positive 3. It started out life in the denominator of the original fraction, and that's where it ends up as well. So if the exponent is positive, then we don't do anything. We leave it alone, right? That's what we want to get at. On the other hand, that's not going to work. On the other hand, if we look at these guys, we had 3 to the negative 8, 3 to the negative 8. It was up in the exponent, it was in the numerator, and then it ended up down here with a positive exponent down in the denominator. And then this one had a negative 2, y to the negative 2, and after a bunch of work, we see that it ends up down here in the denominator, y to the positive 2 power. Right, so we can think of these as getting moved. We always use the language of move it down. So we moved this down here, we moved this down here, and we changed the signs. On the other hand, 2 to the negative 5 started out life in the denominator, and then at the end of the day, it ended up here in the numerator. And then the w to the negative 6 started out in the denominator and ends up here in the numerator, right? So again, we use this language of move it. So we move it up there, and then we move it up there. But the language move it up there sounds a little weird if you don't know why or the reason why you're allowed to do that. But in practice, that's what we do. Okay, so to move any exponential number, make sure everything's being multiplied, right? That's the only way any of this makes sense. Because if they weren't being multiplied, right, if this was like an addition right here, if this had an addition, then all of a sudden we need a common denominator, and it makes things a lot more complicated, right? Subtraction, same thing, too complicated. So we can't have addition or subtraction there. This can only work as long as everything is being multiplied. So if everything is being multiplied, we have a bunch of exponential numbers being multiplied, then we can move that term from the numerator to the denominator or the denominator to the numerator, either way, by changing the sign of the exponent. Good. So let's do one more in this spirit, and then I'll just do it really quickly without having to do the middle steps. So for example, if we had 5 to the negative 8 power, q to the negative 4 power, n to the power of 7, w to the power of negative 3, all over 2 to the power of negative 3, a to the power of positive 5, b to the power of negative 8, and x to the power of positive 11. Okay, so now to simplify this, I just got to go through. Whenever I see here's my game plan. All the ones that have a negative exponent are going to be moved down into the denominator. And all the ones that have a negative exponent that are already in the denominator are going to get moved up to the numerator. That's good. Okay, so I can see that the n to the 7th power, that's not going to move anywhere. That's just going to be up there. And then I'm going to bring up this 2 to the positive 3rd power. I make it a positive because I'm moving it up to the numerator. And I'm going to bring up the b to the positive 8th power. Okay, and now in the denominator, I'll end up with 5 to the positive 8th power, q to the positive 4th power, w to the positive 3rd power, and then this moved up to the numerator. There's an a to the power of 5, a to the power of 5, b to the power of, that moved up there, and then there's an x to the power of 11. Good. Okay, well, traditionally we like to put the numbers out in front, so really I would just switch these, and that would be it. That's about as much as we can do. So all I would do is maybe switch this guy around. I'll just put it back here. And the 7th power. There. So we like to lead with the number part of it. Good. And now, should we actually multiply this out? 2 times 2 times 2, that's just 8, right? So 8 just looks simpler than 2 to the 3rd power. So most people would just change that to 8. But 2 to the 8th power is pretty big. So I think most people would just leave it like this in exponential form. So this would be our final answer. Okay, so those are all the rules that we have to work with, and then we can. So these are all the rules that we looked at. Rule number 1: a to the power of m times a to the power of n. When we have two exponential numbers like this with the same base, we add the exponents. A to the power of m over a to the power of n. Rule number 2 here. Then we subtract the exponents in this order. Right? Here's a nice little example. A to the power of m raised to the power of n. We multiply the exponents. Don't confuse rule number 1 and rule number 3. Right? Pay some attention there. Those two get confused all the time. Then we have this sort of a distribution property that happens here. That's rule number 4. And then the ones I just wrote up there are a little out of order. But they're the same ones we just wrote down, and then the book just wrote these things separately. If a does not equal to 0, and a is a real number and is a positive integer, then we know that a to the 0 power is 1, and then a to the negative n power is equal to 1 over a to the nth power. Right? So these are all the rules we were just looking at. So let's do some examples to simplify a couple of these guys. Okay, so using our rules, by default, if there's nothing there, then that must mean that there's a little 1 here, right? There's one copy of this. This one is being multiplied by a 3, or being raised to the power of 3. So it's 3 copies of this, only 1 copy of those. So for that reason, it's just going to be each one of these is raised to the power of 1. So this is going to be 2 to the power of 1. and a to the third power raised to the power of 1, and b to the second power raised to the power of 1. And now these are all raised to the power of 3, so it would be 3 to the power of 3, a to the power of 3, and then b to the fourth power raised to the power of 3. All right, well, any number raised to the power of 1, that's boring. It's not going to change anything. So that's just going to be 2 times a to the third power times b to the second power times 3 to the third power times a to the third power, and then b to the fourth raised to the third, we know that that must be b to the power of 4 times 3. So that'll be 2 times a to the third power, b to the second power, 3 to the third power, times a to the third power, b to the 12th power. Good. And now we can combine some like terms. So we have a to the third power there and another a to the third power there. Those will combine. And we also have a b to the second power and a b to the 12th power. Those will combine. And finally, we have the numbers. So we have a 2 times a 3 to the power of 3. They will combine. So let me write them sort of next to each other. We have 2 times 3 to the third power, a to the third power times a to the third power times b to the second power times b to the 12th power. That'll be equal to 3 to the third power. That's equal to 27. Times 2 is going to give me 54. Times a to the 3 plus 3 times b to the 2 plus 12. So my final answer is going to be 54 times a to the 6th power times b to the 14th power. Okay, that's about as good as it gets. Here's the author's solution. Exactly the same thing I did. Okay, move on to another one. Okay, what do we do with this guy? Let's distribute the 3. So this is the same thing as x to the third power over y to the third power times, okay, so this will be y squared raised, y squared x, all of that raised to the fourth power, divided by z raised to the fourth power. And then this will be equal to x to the third power over y to the third power times y squared raised to the fourth power x to the fourth power, right? Sort of a distribution. Notice that these are being multiplied, so I'm allowed to do that. And in the denominator, we have this z to the fourth power. I know that these are then going to be equal to 8. We have an exponential number raised to another power. So let me write that one down. So that'll be x to the third power, y to the 8th power, x to the 4th power, all over y to the third power, z to the 4th power. All right. So simplifying this, in the numerator, I have these two, this one and this one. They're exponential numbers with the same base. I know that I can simplify them by adding the exponents. And I also have these two, which are exponential numbers with the same base. I know I can simplify them by subtracting the exponents. So this is going to be equal to x to the 3 plus 4 times y to the 8 minus 3 times 1 over z to the 4th power. Right? You can also think about putting a 1 underneath each one of these if it makes you feel better. Good. All right, so this will be equal to x to the 7th power, y to the 5th power, times 1 over z to the 4th power, and finally x to the 7th power, y to the 5th power, all over z to the power of 4. Okay, so here's your author's solution for this one. Same thing I did. All right, here's another example. Eliminate the exponent, eliminate the negative exponent, simplify this expression. Okay, so we could go through the longer version of this, right? So the longer version of this would be to rewrite each one of these as a 1 over t to the positive 4 and a 1 over, right? So let's begin the longer process. The longer process would be that this is a 6 times an s times a 1 over t to the positive 4th power. To deal with all of these, we'd have to put a 1 underneath them. And then down in the denominator, we'd end up with a 2 times a 1 over s to the power of 2 times a t squared, which would then be 6s over t to the 4th power in the numerator, divided by 2t squared divided by s squared in the denominator. And now we multiply the numerator times the reciprocal of the denominator, 6s over t to the 4th power times s squared over 2t squared. Good. And then we combine like terms, and we have an s to the power of 1 here, s to the power of 2 there. We know that that's going to be equal to 6s to the power of 1 plus 2. We add them. And then here we have a t to the 4th, a t to the 2nd. This will be equal to 2 t to the 4 plus 2 power. So we'll end up with 6s to the power of 3 divided by 2 t to the power of 6. Okay, so that would be the longer way of doing this, right? The easier, faster way would be to recognize our little shortcut so we don't have to go through this process and say that from the beginning, let me recopy the question, 2s to the negative 2t squared, I'll put a big or. Starting from the beginning, we know the shortcut. If we have a negative in the exponent, we just move it from the numerator to the denominator or from the denominator to the numerator. And so just moving it down, here's my game plan. I'm going to move this guy down and I move this guy up. So I'll end up with one big fraction where there's a 6 in the numerator, there's a t squared, there's an s there, and there's a t squared there. They don't move. This guy stayed the same. They don't have a negative exponent. And this, oh, there's a 2 there as well. This stays, that stays. So it's really just these two that need to flip around. So there'll be an extra s squared that comes from here up to the numerator. And there's an extra t to the 4th that just moves down. Right? That's just following our rules. And now we simplify it, and we'll get the same answer. 6s to the 3rd power all over 2t to the 6th power. Right? Okay, of course, we can also reduce this. 6 divided by 2, that's just equal to 3. So this is 3s to the 3rd power divided by t to the 6th power. Which is the same thing over here, we can reduce that. 3s to the 3rd power over t to the 6th power. Okay, so this is the author's solution for that one. Okay, moving on to this one. Okay, again, we have a nice little shortcut for this one, so let's just go ahead and apply it. If you remember, one of our shortcuts said that if we have a fraction being raised to a negative exponent, that's equivalent to finding the reciprocal of the fraction being raised to the power of a positive exponent. That was one of our rules. So this is just going to be equal to 3z to the 3rd power divided by y, and the whole thing is being raised to the power of 2. That was one of our rules. So now we can distribute that, and we end up with 3 squared times z cubed squared all over y squared. And now we have an exponential raised to another exponent. That'll be 3 squared z to the power of 6, right? We multiply the exponents, and then divided by y squared. Good. 3 squared is a 9, so I think most people would just go ahead and multiply that out and get 9 z to the 6th power divided by y squared. I think that would be a good place to end with this one. Good. 9 z to the 6y. Okay, so here's the author's solution, identical to mine. Okay, so scientific notation. What is scientific notation? Scientific notation is a way to write either very large numbers or very small numbers in a way that's more manageable. And we do that by following this rule. A positive number x is said to be written in scientific notation if it is expressed in as follows. So x equals to a times 10 to the power of n, where a is a number that's greater than or equal to 1 but less than 10, and n is an integer. Okay, so what are we doing here? We're looking at powers of 10, so we're going to take advantage of powers of 10, and we're going to express either a very large number or a very small number this way. So, for example, if we had 3,500,000, what we want to say is that this can be expressed as 3.5 times 1 million. And then 1 million is something that can be written as a power of 10. So this 3.5 can be written as 10 to the power of, and remember to write this as powers of 10, we count the spaces. So 1, 2, 3, 4, 5, 6 spaces. And it's a nice pattern that happens with powers of 10, right? Let me refresh your memory on that in case you forgot. So here's powers of 10. If we have 10 to the power of 1, obviously that's just 10. 10 to the power of 2, that's 10 times 10, that's going to be 100. 10 to the power of 3, well, that's going to be equal to 10 times 10, that's 100, times another 10, that's 1,000. So we have 1,000 there. And if we multiply 10 to the power of 4, we end up with 1,000 times another 10. That's going to be equal to 10,000. So we start seeing this really nice pattern. The number of zeros, 1, 2, 3, 4 zeros, equals the exponential number. 3 zeros, a 3 there. So it doesn't take a lot to guess what the answer would be if we had 10 to the power of 8. 10 to the power of 8 is just going to be 1 with 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And then we can come back and put commas. 1, 2, 3, 1, 2, 3. 100 million. 10 to the 8th power is 100 million. Okay, what about in the other direction? Well, obviously, 10 to the 0 power is just going to be 1. And we know that 10 to the negative 1 power, that's going to be 1 over 10, which is equal to 0.1. And if we keep going over here, 10 to the negative 2 power, well, that's going to be equal to 1 over 10 squared, which is equal to 1 over 100, which is equal to 0.01. Okay, so we start to see a little pattern there as well. If we take a 1 and we move it to the left by 1 space, we get this minus 1. And if we take the 1 and we move it over 1, 2 spaces, that matches up with that guy. Okay, so it doesn't take a lot to realize what happens if we keep going this way. What is 10 to the negative 5 going to be? Well, that's going to be equal to, start off with a 1 and then move it over 1, 2, 3, 4, 5 spaces, which means we have to introduce 1, 2, 3, 4 zeros. 0.00004, right? 4 zeros in there. Okay, so that's the pattern that we're going to be using. Zoom out a little bit more. So that's the pattern of tens that we're going to be using in order to write a number in scientific notation. So whenever we see a number in scientific notation, A couple of things. Keep in mind that we go back to old school. This little x here represents multiplication. So that could be a little confusing since now that we're deep into algebra, we know x represents a variable. But in scientific notation, we still leave that little x there to represent multiplication. So it's going to be a multiplication of two parts. We take the number that's either really big or really small, and we're going to separate it into two pieces. One of them is going to be a power of 10, right? And then the power of 10 falls under this very nice pattern. And so if we have a negative in the exponent, we're going to end up with a small decimal value, like 10 to the negative 5 is a small decimal value. And then if we have a positive in the exponent, that means we're going to end up with a very large number, like 10 to the 8th power, that's 100 million. Okay, so keep that in mind, keep that pattern in mind as we go back and forth with scientific notation. And then the leading number, this other part, we've chosen it to be a number that's bigger than 1, but less than or greater than or equal to 1, but strictly less than 10. So what that means that it's going to be some decimal number where there is going to be a 1 decimal something over there, or it could be a 2. So this guy could be a 2. Right? Or this guy could be a 3, right? So whatever this is in here, it's whatever this is in here, we can stick a 1 or a 2 or a 3, all the way out to 9, right? So it's 1 point something, 2 point something, 3 point something, 4 point something, right? All the way up to 9 point something, but we can't let it be a 10. 10 point something wouldn't work. Okay, so it's got to be some decimal number. Another way of thinking about that is on the number line then. Here is the number line, here is 0, here is 1. We're not letting this value a be somewhere in there, no. 1, that's 2, that's 3, that's 4, that's 5, 7, 8, 9, like this. Here's 10. We're requiring that value to be either 1 all the way up to, but not including 10. So it's got to be a number in this part of the number line. Some decimal number that's bigger than 1, but strictly less than 10. Bigger than or equal to 1, but strictly less than 10. The a value has to be somewhere in here. That's that leading value there, times some power of 10. Okay, let's look at a couple of examples. So, for instance, when we state the distance to the star Proxima Centauri is 4 times 10 to the 13 kilometers, the positive exponent 13 indicates that the decimal point should move 13 places to the right. Okay, so remember that 10 to the power of 13 is 1 with 13 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros. So that is a really, really big number, right? Which is what we would expect. How far away is the nearest, I think it's a galaxy, right? Oh, not a galaxy, it's a star. For instance, when we state the distance to the star, so it's I think it's the closest star to us, that's still pretty big, right? It's pretty far. So 4 times 10 to the 13 is equal to 4 times this 1 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros. Put a comma there, put a comma there, put a comma there, put a comma there. Okay, 4 times this, that's equal to this guy. Right? Okay, well, the shortcut is then the pattern that we notice is that if we just take the 4, we start off with this. Here is the 4 times, and then this is the one we're going to move over 13 spaces. So 1, 2 spaces. which means we introduce 13 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And so that's how we end up with this. Okay, so move the decimal to the right. Okay, so just keep in mind of whether we are expecting a very large number as the final answer. If this is a positive exponent, we should be expecting a very large number. On the other hand, if this is a negative number in the exponent, we would be expecting a small number. Right, so for example, when we state that the mass of hydrogen atom is 1.66 times 10 to the negative 24 grams, the exponent is negative, we expect that to be very small. Right, just looking at that by itself, 10 to the negative 24 is equal to 1, and then we're going to move this decimal over 1, 2, 3, 4, 5, right? We keep going that way 24 times. So the first time we don't have to introduce a 0, that's going to be 1, but then every time after that we introduce a 0, so that means that we have to introduce 23 zeros, right? 1, 2, 3, 4, 5, 23 different times. So 0.00000 with 23 zeros. 23 zeros. Right, that's very, very small. Good? Okay, so the pattern for this guy is to start off with this. We have the 1.66 times 10 to the negative 24. I'm expecting my final answer to be very small, right? Because I'm multiplying this number times something that's very small. So the final answer will be very, very small. So we take the 1.66, and then we're going to move this decimal over once, right? The first time, we don't have to introduce a 0. But then after that, we do, right? So then this is going to be 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So we keep going. And so we're going to end up with 23 zeros. That's what this is. Let's count them. That's going to be 1, 2, 3. Well, that's ugly. Let me zoom in a little more. That's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 zeros. Okay, so that's our final answer. 0.0000000, 23 zeros, 166, which is an incredibly small number, right? That's the whole point of this. Scientific notation makes it possible for us to write down incredibly small numbers in an easier way, or incredibly large numbers in an easier way. All right, now let's take a look at a couple of examples. Let's say, for example, we're asked to write each of these numbers into scientific notation. So we have 56,920. Not terribly large, but it'll give us a good practice on this process. So we have, let's work on that one first. We have 56,920. Remember that by default, that means that the decimal is back here. Okay, so in order for us to rewrite this into scientific notation, we have to write it into two parts. The first part must be a number that's trapped between 1 and 10, inclusive of 1, not inclusive of 10. So here's 1, here's 2, here's 3, and all the way out here, there's 10. Okay, so it could be any number that is inclusive of 1 all the way out and all the way out to 10. Right, that's just what we've agreed to in math. That's how scientific notation works. 56,000 is definitely not in that little interval. So we have to start moving the decimal over. If I move it to the right, well, it's just going to get even bigger, and that's not going to be in that interval at all, right? So I have to move it this way. Okay, so if I move it a little bit closer to the left, ignoring that first 0 then, now it would only be at 5,000 and something. Still not in that range. Move it over again, and I'll be at 569.2. Nope, that's not in there. If I move it over again, I'll be at 56.92. Still not in that range. And finally, if I put it right in there, I end up with 5.56920, but I have a point right there. And that one is in here. 5 point something is in here, 5.692. So that satisfies that first part of the scientific number. That first number has to be in this range. The next thing is that I have to multiply it by a power of 10, 10 to the power of something, so that it equals that original number. So let's think about what that is. We have to figure out what this is. 56920. 56,020 is equal to, and it's going to be this multiplication. Now this number is much smaller compared to that one, right? So if I multiplied a small times another small number, it wouldn't make sense that somehow that equals a really big number. So the only way that this equality can stay true is if this small number, this 5 point something, is multiplied by a very large number, such that the multiplication of these two gives you that big number, right? So we moved it over 1, 2, 3, 4 spaces. So there's two good candidates that people often get confused by. There's that guy, and then the other thing that people often confuse is, well, is it one of those negatives? 2 times 10. So the other popular answer to this is -4. So I know that there's rules about when you go left and you go right, and then positives and negatives, and you could just stick to those rules if that's what makes sense to you. But if you just pause and kind of take a step back and think about it, one of these is obviously true, and the other one can't be true. Remember that this means that it's 10 to the power of 4. This means it's 1 with 4 zeros behind it. This is a large number. 10 to the -4, that means that this is going to be a very small number, right? A very small little decimal value. So does it make sense that 5 point something times a very small decimal somehow equals 56,000, right? Hopefully it makes no sense, right? So hopefully it's clear that this one can't be the answer. This one makes more sense. 5 point something, 5.692, is much smaller than 56,920, but when we multiply it by this large number, then it does make sense, and then they become true, right? So this is the true statement. Good. Let's look at the other one. Again, we have 0 point, and now there's 1, 2, 3, 4 zeros. 1, 2, 3, 4 zeros, and a 93. And of course, this decimal value is very, very small. It's not in that range. So we got to move it over 1 space, 2 spaces, 3 spaces, 4 spaces, 0.93. That's going to be over here somewhere, right? So that's still not good. That's a very popular place for people to stop, but we can't stop there. We got to go one more. 9.3. Yeah, that's in here. 9.3 is somewhere over here. 9.3. We can't go one more. If you go one more, then you'll be at 93, and 93 is way out there somewhere. So it definitely has something to do with a 9.3. So again, if you write down the whole thing as a complete sentence, I think it's clear what the right answer should be. There's 4 zeros, then a 9.3, a very small number. And we're saying that that's equal to a 9.3, which is a really big number compared to that one, times 10 to the power of something. So again, there's two popular candidates, 1, 2, 3, 4, 9, 3, equals to 9.3 times 10, 10. So the two popular candidates, well, we moved the decimal 5 times, so it has something to do with that. So one candidate is to put a 5 there, like we did up there, and the other one is to put a -5, right? So which one is it? Remember that 10 to the 5th power, that's a pretty big number. So we have 9.3 times a large number, and somehow that equals this tiny little decimal. Hopefully that makes sense that, that can't possibly be the answer. This one's got to be it. 10 to the -5, that's going to be a very small decimal. And when we multiply that tiny little decimal times 9.3, which is a pretty large number compared to that one, the product of those two does equal that little one, right? So hopefully you can just kind of reason your way through it so you can figure out whether you're supposed to have a positive exponent or a negative exponent. Otherwise, if you just want to go through and memorize all those rules about when you move the decimal to the left, when you move it to the right, then it's something to do with the negative and the positive exponents. To me, that's more confusing than just to simply write it out and take a second and think about when it makes sense, right? So if the final output is very large, I expect that to be a positive, right? And if the final output is a very, very small decimal, then I expect that guy to be a negative. Okay, hopefully that makes sense. Moving on. Oh, so here's the author's solutions. We moved it 4 decimal spaces to the left, therefore we write it as 5.692 times 10 to the 4th power. We moved the decimal to the right, 5 spaces, therefore that's going to be equal to 9.3 times 10 to the negative 5 power. Okay, moving on, radicals. So we know that 2 to the nth power means whenever n is an integer, sorry, we know what 2 to the nth power means whenever n is an integer. To give meaning to the power, such as 2 to the power of 4/5, right? What if we had a fractional exponent? We're happy with this guy as long as it's a counting number, like if n equals to 1 or 2 or 3 or 4 or 5, dot, 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 then things make sense, right? 2 to the first power, we know that's just 2. 2 to the second power, we know that's just 4. 2 to the third power, we know that's just 8. So we're happy as long as with the exponent in there is a nice counting number. We just expanded our idea of that to include integers. So now we know that also 2 to the 0 power, that's just going to be 1. And 2 to the negative 1 power, that's just going to be 1/2. So we're okay with having 2 to the power of anything as long as that thing that goes in there is either a 0 or a 1 or a 2 or a 3 or a 4, dot, 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 dot. Or it could be a negative 1, or it could be a negative 2, or it could be a negative 3, right? So we're happy with all that. But what if it was a fractional power, right? What does that mean? 2 to the power of 4/5. That's ugly. What if it was another decimal? What if we had, what if we had 2 to the power of 0.25? What do we do there? Right. So that's what we want to tackle. Before we get to that, though, we're going to explore what this symbol means in a little more detail. We've worked with it before, a radical. So this symbol means the positive root of, thus the square root of a is equal to b. This means that b squared is equal to a, and that b must be positive, must be greater than or equal to 0. Right? That's the definition of what this means. So, for example, since a equals to b squared has to be a positive answer, right? So whenever you take any number and you square it, you get a positive answer. So a equals to b squared. Then the symbol, the square root of a, makes sense only when a is positive. So we're only dealing with cases where we have the square root of a positive number. That's what this is saying here. So if we want to figure out what is the square root of 9, for instance, the answer is 3. And why is it the answer 3? Well, that's because 3 squared equals to 9. Right? In other words, if we wanted to figure out what is the square root of 25, well, the answer is 5. Why is it 5? Because 5 squared equals to 25. Right? Well, what if it was something we didn't know, like what's the square root of 3? The square root of 3 is some decimal number, and I don't know what that decimal number is. If I had a calculator, I can figure it out. But it's some decimal number a, right? And what's special about a? Well, that decimal number a, well, that's because a squared, right? It's going to be that decimal such that a squared equals to the square root of 3. Right? That's what it is by definition. Good. Okay, so square roots are a special case of the nth root, right? So in other words, whenever we see this square root, by default, we have in mind that there's this little tiny invisible 2, right? It's the square root of it. There's this little invisible 2. By default, if you don't see anything there, we're dealing with 2. But that's just one case of a larger situation where we just have the nth root, right? Where we have the square root, the cube root, the fifth root, doesn't matter, the nth root. So if n is any positive integer, then the principal nth root of a is defined as follows. The nth root of a equals to b means, by definition, that it must be true that b to the power of n is equal to a, right? If n is even, we have that a and b both must be positive, and if n is odd, then that's not the case. So, for example, what is the cube root of 27? Cube root of 27, right? Well, this is 3. And why? Because I know that when I take this guy, 3, and raise it to the power of 3, I get 27. Right? That's what this is saying. The answer to this is some number such that when I multiply it by itself 3 times, I get 27. On the other hand, what if we had the fourth root of 81? Well, guess what? The answer is also 3. Why? This is because 3 to the power of 4 equals to 81. Okay? All right, so some properties of roots. The nth root of a times b is equal to the nth root of a times the nth root of b. So this first property is telling us that we can separate it, right? It can separate it into multiplication of 2 different roots, and we keep the index of the root for both of these. So here's an example. We have the cube root of, and then inside the root, we have negative 8 times 27. So we can separate it into 2 separate radicals where we have the cube root of negative 8 times the cube root of 27. Okay, so this is just letting us know we're allowed to do that. We're allowed to separate it, and that's as long as we have multiplication inside here. Keep that in mind, that between the a and the b there's a multiplication. But if we have a fraction, a over b, inside the nth root, then this rule says that we can separate it and have the nth root of a in the numerator, the nth root of b in the denominator. Okay, so here's an example. 16 over 81 inside the fourth root. We can separate it as the fourth root of 16 divided by the fourth root of 81. Right? And the fourth root of 16, find a number such that when you multiply it by itself 4 times, it equals to 16. That's got to be a 2. And as we looked up there, the fourth root of 81 is a 3. This one's a little bit trickier. The nth root of the nth root of a is equal to the m times nth root of a. So let's see if we can explore why that is. Consider, for example, if we had the cube root of the square root of 3. How can we simplify that? Let's start with the outside. Wait, have we established the root thing? Yeah, we'll come back to this because I need to do something. Never mind. We'll come back and show why that is in a little bit. Okay, the nth root of a to the n is equal to a. In other words, a to the n and the nth root undo each other, the inverse operations of each other, and you get back to the value of a if n is odd. So here's an example. N is odd, the 3. The cube root of negative 3 to the power of 3, these two operations are inverses of each other. They undo each other, so we just get a negative 5. Okay? And that's true as long as we have n equals to odd. If, on the other hand, n is even, then it's not true that they just give you a. This is, in fact, a way of defining the absolute value function. So, for example, let's say n is even. say n equals to 4. And I have the fourth root of something raised to the fourth power. What's going to happen when I input a positive 2? 2 to the fourth power is going to be equal to 16. And then I want the fourth root of that number. So if I input a 2, the output is still going to be 2. Right? It's going to be the fourth root of 16. And then the fourth root of 16 equals to 2. So I get the same answer. What if, on the other hand, I input a negative 2? Negative 2 goes in, and then negative 2 raised to the fourth power is going to give me positive 16, right? Because we're raising to the power of 4, so that's going to be a positive 16. So we'll have the fourth root of positive 16, and so the answer is going to be positive 2. Notice that if I input a positive number, I get a positive number. If I input a negative number, I get a positive number. Doesn't that look just like absolute values? Right? If you think about absolute values, they work the same way. I have an absolute value here. If I input a negative 2, the output is going to be positive 2. If I input a positive 2, oops, the other way around to match with this thing. If I input a negative 2, the output is going to be positive 2. If I input a positive 2, the output is positive 2, right? So that's what an absolute value function is going to do, and that's what this does, right? So that's why we define absolute values this way. Good. Okay, so almost done with this section. Let's just do a couple more things to simplify this. All right, how do we simplify this guy? Okay, so what we could do is we can break this up into the cube root of x to the third power times x to the first power, right? X to the fourth can be broken up this way. And we also know that we can rewrite this as x to the third, cube root of x to the third times the cube root of x to the first power. Our properties tell us we can separate it this way. And the cube root of x cubed, that's just equal to x times, and well, this doesn't simplify, so we'll just rewrite it as the cube root of x. Okay, so this is equivalent to this. So this is the reason why, but in practice, I like just to think about that we can pull out one copy of x as long as the exponential power matches the index of the root. So we can pull out one x, and then what's left over is just one copy of x inside the radical. Good. So x root x, cube root of x. We keep the same cube. Or another example, if we had the cube root of x to the 11th power, well, let's not make it 11, 17th power. But if there was 17 in there, well, if we do it the long way, then we can separate this into groups of 3. X to the third times x to the third, that takes care of 6. That takes care of 9. That takes care of 12. That takes care of 15. And now there's an extra x squared that remains. All of that is inside this cube. And now we can separate it like this and have each one of these represent one copy of x times cube root of x to the third times cube root of x to the third. It's 1, 2, 3. There's 2 more. Cube root of x to the third. Cube root of x to the third, and finally cube root of x to the second. And now each one of these represents an x, so that's just going to be x, that's just going to be x, that's going to be x, that's going to be x, that's going to be x. So we end up with 1, 2, 3, 4, 5 copies of x that come out of the radical. And we still have x to the second power inside the radical. So our final answer is going to be that the cube root of x to the 17th can be simplified as x to the power of 5 cube root of x squared. Okay, so you can see how a shortcut to this would just be to think about how many groups of size 3 I can pull out of this. I think of like, when I first learned this, I remember I was told to think about this as like a little schoolhouse, and we have 17 little kids in there, and they're going to go on a field trip. They got to leave the schoolhouse, but they got to hold hands, little groups. How many little groups can we get? So 3 of these x's can hold hands and come out as one single x. And how many different groups are we going to get? Well, that's going to be 5 different groups. That takes care of 15 of these x's. And then there'll still be 2 inside the schoolhouse, and they cannot come out because they don't have a group of 3. So 2 of them get stuck inside. Right? So that's a little way to think about it as a shortcut for it. Okay, that's the author's solution to that very first one. Let's try one more. So the first thing I would do here, simplify this, is to break down that 81. So we know that 81 breaks down as 9 times 9, and the 9s break down as a 3 times a 3, and another 3 times a 3. So that means that 81 is really equal to 3 to the 4th power. So let's introduce that into here. So that's 3 to the 4th power. And we have x to the 8th power, y to the 4th power. All of this is inside the 4th root. Okay, so I'm going to rewrite this as the 4th root of 3 to the 4th power times the 4th root of x to the 8th power times the 4th root of y to the 4th power. And then just to have these match, I'm going to rewrite it this way. This is the 4th root of 3 to the 4th times x squared raised to the power of 4. And then this is the 4th root of that times the 4th root of y to the 4th. Okay, so because the index matches the exponent and they're even, right, 4, then here, well, we just get this number. It's just going to be 3. 3 raised to the 4th power, that's going to be 81. And the 4th root of 81, well, that's just 3. Okay, all right, now here we have this number raised to the 4th power. It matches that guy. So that's just going to bring this down and give me this. But remember that when they're even, when the index is even, then it really ends up being the absolute value definition. So it's the absolute value of x squared times, and it's going to be the absolute value of y. Right? Remembering our definition for absolute values. Good. But now x squared is always going to be positive, so this is just kind of redundant. I don't need to wrap it around absolute values because you're always going to get an absolute value and a positive answer after you square it. So our final answer is just going to be 3x squared absolute value of y. Good. 3x squared absolute value y. Okay, next example, and I think I had made a mistake when I copied this. So this should be 200 in here. So let's rewrite it. This is root 32 plus root 200. Okay, so in order to add these two, let's break them down and simplify them as best we can. So 32, we know that that's going to be 2 times 16, which is going to be equal to 2 times 8, which is equal to 2 times 4, which is equal to 2 times 2. That's going to be 1, 2, 3, 4, 5.
That's going to be 2 to the 5th power. And 200, we can break that down into 2 times 100, which then breaks down into 10 times 10, which then breaks down into 2 times 5 and 2 times 5. So there are 1, 2, 3 powers of 2. This is equal to 2 to the power of 3 times 5 to the power of 2. Okay, so this is going to be the square root of, and we have 2 to the power of 5 plus square root of, and we have 2 to the power of 5, 2 to the power of 3 times 5 to the power of 2. By default, even though it's not written there, the little index here is a little 2, right? If there's nothing there, then by default it's a 2. So let's think of our shortcut. We can pull out copies of 2, right? And they have to group up in little groups of 2. So I can pull out one of them, and then that'll be, there's 3 remaining inside. And then 2 more group up, and they come out, little groups of 2. So I'll have another 2 out there. And there'll be 1, 2 remaining inside the radical. Square root of 2. Okay. Over here, only 1 copy of the 2 can come out, so plus, and let's say 1 copy of the 2 comes out, and there's going to be 1 more 2 inside there, and then 1 copy of 5 can come out. Oops, let me put it in. Root 2. Right, so 5 squared, and then there was square root. These 2 operations cancel. There will be 1 power of 5 that comes out. And then 2 times 2 is 4. We can pull out 1 copy of 2. There's 1 remaining. Good. Okay, so then this simplifies to 4 root 2 plus 10 root 2. And now, depends on how you look at this. We can either factor these 2. So the thing about it is 2 plus 10, and then I factor out the root 2, right? It's the reverse of distribution. That's how I get that. Or you can just simply think about the fact that these 2 are of the same type. 4 copies of root 2 plus 10 copies of root 2. Together, they're going to give you 14 copies of root 2. Good. And that's our answer for this one. Let's see what the author did. 14 copies of root 2. Okay, same thing. All right, if b is greater than 0, so positive, we have this. Okay, so again, by default, this must be this little invisible 2 that goes in there, little invisible 2 that goes in there. So this will be equal to 5 root b minus b root b, right? Because 2 of them come out, and there's only 1 b stuck inside there. And now, again, they're of the same kind. 5 copies of this root b minus b copies of this root b. We can also factor it out, and so this is 5 minus b, and then root b will be our final answer. It's as good as it gets. Oh, I didn't mean for the answer to be here. Okay, well, oops. This guy. Okay, so looking inside the radical, we can factor out that 49. So we'll have inside the radical, we can factor out a 49, giving me an x squared plus 1. And now we can separate this into the root of 49 times the root of x squared plus 1. And the root of 49 is just equal to 7. So it's 7 times the square root of x squared plus 1. Again, that's as easy as it gets, as far as it goes, right? So that was this guy right here. Okay, so rational exponents. Almost done with this section. Back to having this fraction in the exponent. So let's think about what it means to have a to the power of 1/3. What does it mean to have a to the power of 1/3? A to the power of 1/3. What is that? Well, if we raise it to the power of 3, then we know from our work with exponential numbers that this must mean that it's a to the power of 1/3 times 3. Put a little 1 there. That means that these guys cancel. So it gives you a to the power of 1, or just a. Okay? So a to the 1/3 is a value such that when you raise it to the power of 3, we get the value that's inside there. Well, isn't that the same thing as this? If I have the cube root of a and I raise it to the power of 3, don't these two operations undo each other? And we end up with exactly with whatever is inside there, principally a, right? So if I take, for example, 27, 25, 125, and I find the cube root of it, well, that's just going to be 5. 5 times 5 is 25, times 5 is 125. That's going to be an answer of 5. And so now if I take that and raise it to the power of 3, well, then that's just going to give me the 125. Right? So it doesn't matter what this is inside here. There's nothing special about the 125. No matter what I start off with, whether it's 125, whether it's 100, take the cube root of 100, whatever that is. It's some decimal number. And now raise it to the power of, it's some decimal number such that when you raise it to the power of 3, we get 100. That's the definition of it, right? And so if we do raise it to the power of 3, we're going to get 100. Right? These two operations undo each other. Right? That's what this is saying. These two operations undo each other, and we get whatever is inside here. This will be the exact same thing. They match. Right? But we just established that this behaves the same way. When I raise this to the power of 3, I get that this is exactly that. It's behaving the same way. So what we want to conclude, the point of this, is we want to establish that this fractional is the same thing as this radical. That the two notations really mean the same thing. That's what we're driving at. Okay, and that's what they're doing here in general. A to the power of 1 over a to the 1 over n power raised to the nth. These two n's cancel, so we'll end up with a to the 1 power, which is equal to a. Okay, and then that behaves in the exact same way as our definition for roots. Remember, roots were this. If we were trying to figure out what this is, what's the nth root of a? Well, we'll go, okay, well, if the answer is b, such that b to the power of n equals to a. Good. Okay, so what we want to conclude from this is this guy right here. That's what we want to draw from it. A to the 1 over n equals to the nth root of a. Hopefully my little explanation with this one is convincing enough. But if not, it's just one of those things we have to memorize. So here's our how we're going to use that. So if we have some fractional power, a to the power of m over n, we want to say that this is equal to a to the power of either 1 over n times m. That's one option. Right? We can separate that fraction into that, which means that this is equal to a to the 1 over n, and then the whole thing raised to the mth power. And now this, we just established that that's the nth root, so we can say that that's equal to the nth root of a raised to the power of m. And that's what this one is saying. A to the m over n is equal to the nth root of a raised to the power of m. Okay? Or, likewise, if we have a to the m over n, we can also say that this is equal to a to the power of m times 1 over n. And all I did was switch the order around. We could do that. which means that this is equal to a to the m, and then the whole thing raised to the 1 over nth power, which means that by newfound description, this fractional means that this is the nth root of a to the mth power. Good. Okay, so we have two options. When we have a fractional power like this, we can either use this description of it, or we can use this description. And all of it at heart is really accepting that this is true. Right, so an example of this, just to make sure it's clear, 5 to the power of 1/3, that's the same thing as the cube root of 5. Right, that's what this notation is saying. Or 7 to the 1/2 power is the same thing as the square root of 7. Good. Okay, so hopefully that makes sense. Let's use everything we've learned to simplify some of these things. So we have fractional exponents, but all the same rules we learned before about exponents stay the same. We have two exponential numbers with the same base being multiplied. This is just going to be equal to a to the power of 1/3 plus 7/3. They have the same base, so we add the exponents. This is going to be equal to, now luckily these fractions already have the same denominator, so this would be equal to a to the power of 8/3. Good. Okay, now this one, we have three exponential numbers. They all have the same base of a, and we know that when we multiply them like this, we add the exponents, and when we divide it, we subtract. So this is just going to be equal to a to the power of 2/5 plus 7/5 minus 3/5, which will be equal to a to the power of, and luckily they all have the same denominator, so it'll be equal to 2 plus 7 minus 3 all over 5. So that'll be 9 minus 3 is 6, so a to the 6/5. A to the 6/5. And now, well, yeah, I'm not sure how they're going to want you to leave these. If we went ahead and converted them into a mixed number, this would be a to the power of 2. It goes into it 2 whole times, and then there's 2/3 remaining. And then here, this would be equal to a to the power of 1, and then 1/5 remaining. Good. Okay, this one then can be separated as a to the 2 plus 2/3, right? Because this is a mixed number in here. Mixed number. And we know that that must mean that we can separate this as a squared times a to the 2/3 power. And we just learned that we can rewrite this in one of two ways. So we want to separate this as a squared and then the cube root of a squared. So I'm not sure whether they want you to stop here or they want you to expand it out and maybe get to there. Okay, let's continue to expand this one, see if it makes sense. So let me bring this over here. We have a to the 1 and 1/5 as a mixed number. So this is going to be equal to a to the first power times a to the 1/5 power, which is equal to a times the 5th root of a. Right? So again, I'm not sure if they accept this as your answer or is this the answer. They're both good, right? Okay. Let's see what the author did here. their solutions over here somewhere. Oh, okay, so they just stopped there. A to the 3 over 2 power, a to the power of 6 over 5 power. Okay, so we took it a little farther. That's okay. Okay, moving on then. Let's simplify this one. We have that this is equal to 2 to the power of 3 over 2 times a to the third power raised to the power of 3 over 2 times, and then b to the fourth power raised to the power of 3 over 2. This is equal to the square root of 2 to the third power, and write it that way, times, and this is equal to the square root of a to the third power raised to the third power, and this is equal to the square root of b to the fourth power raised to the third power inside the radicals. So here, again, we can use our shortcuts. They come out in groups of 2. So this will be 1, 2 comes out, and there's still a square root of 2. I'm not going to put the little index there because by default, if nothing is written, we know that it's a 2. Okay, here we have the square root of, and this is going to be equal to a to the power of 9. We multiply the exponents, times the square root of b to the power of 12. Okay, so this will be 2 root 2. And then this guy is going to be equal to, well, we can pull out a bunch of a's. We can pull out a to the power of 4. We can pull out 4 copies of a, and there's still one more a inside there. So it'll be the square root of a. And so this becomes b to the power of 6, right? Because we can pull out 6 little groups of b, paired up by this little 2. Good. Okay, so that would be a good way to leave it, although I think that maybe we've gone too far. This is good. We can group up the 2, the a, and the b and get 2a to the fourth b root 2a. And bring them together since they both have root 2, and they're being multiplied. So that's one good answer. Or I think if we had just gone over here, or I think the author of the book was just looking for something simpler, to just multiply these guys out and end up with 2, or this is just 2 to the power of 3 over 2, times, and then we multiply those two together, and we end up with a to the power of 3 times 3 over 2, times b to the power of 4 times 3 over 2, and so we end up with 2 to the power of 3 over 2 times a to the power of 9 over 2 times b to the power of 12 over 2, which then can just reduce by reducing that guy, and we end up with 2 to the 3 over 2 power times a to the 9 over 2 power times b to the 6th power. So this is equivalent to that. I'm not really sure which one the author wants, but I have a feeling it's that one, so say equal. Hopefully it makes sense why both are the same. Okay, moving on. So this 3 applies to each one of these terms, and then by default, if there's nothing there, there's a little 1 there, right? So this is going to be equal to 2 to the third power times x to the 3 over 4, and that whole thing is being raised to the third power, all over y to the 1/3, and all of that is being raised to the third power, times y to the 4th power over x to the -1/2 power, Okay, so that's going to be 2 to the third power times x to the 9 over 4 power, dealing with these two, multiplying those two. And then in the denominator, when I multiply these two, this times this, those two cancel, giving me just a y. So that would be just y there. Times, and then I have a y to the 4th power there. And I know that if I have a negative in the denominator, I can get rid of that negative by moving it up to the numerator and changing the sign. So I'll have another times x to the positive 1/2 power there. Good. Okay, so now I'm going to reduce this. The 2 to the 3rd power, that's not going to go anywhere. That's 2 to the 3rd power. And then I have a y to the power of 1 and a y to the power of 4. Those will reduce. That's equal to y to the 4th power minus 1, or just y to the 3rd power, times x, and I'll have an x to the 9 over 4. And then when I have two exponential numbers with the same base, we add the exponent, so that'll be plus 1/2 there. Okay, so this is going to be equal to 2 to the 3rd power, y to the 3rd power, x to the power of, and now I got to get a common denominator in the exponents. Let's make that a 2 over a 2, common denominator 4. So I'll end up with x to the power of 9 over 4 plus 2 over 4, which then ultimately gives me 2 to the 3rd, y to the 3rd, x to the power of 11/4. So that's pretty good, or you can wrap these up, since they're both being raised to the power of 3, and write it as 2y raised to the power of 3, x to the power of 11/4. So that could be a good answer there. Either that one or that one. Let's see what the author did. 9 over 2. Oh. So the author for this one did something very similar, except maybe just rewrote this as the cube root of 8. I'm sorry, the square root of 8, which then simplifies to pulling out a 4, so that's going to be equal to 2 square root of 2. Times a to the 9 over 2, b to the 6th power. Right, so that's what the author did there. So that gives you this. 2 root 2, a to the 9, 6. Okay, so that was that one. And then, okay, so and then here, what they did is just separate this, so actually multiply this out, just to make it match. So 2 to the 3rd power is 8, so 8y to the 3rd, x to the 11/4. That also matches. Right, so there's lots of different ways of presenting this, and they all are equivalent to each other. Okay, almost done. Rationalizing denominators in standard form. So it is often useful to eliminate the radical of the denominator by multiplying both the numerator and denominator by an appropriate expression. This procedure is called rationalizing the denominator. So for instance, if we have 1 over root a, and we want to get rid of the radical in the denominator, then what we would do is to multiply both the numerator and denominator by root a over root a, which is another version of 1. Right? So we're saying that, this 1 right here is equivalent to this. But now if we multiply the denominators, root a times root a just gives you a. So we end up with root a over a. Now I know that root a over a looks more complicated than just 1 over root a, so there doesn't seem to be a reason for it. But the reason is we managed to eliminate the radical from the denominator. That's all. So for example, if we were just simply trying to simplify 1 over root 3 and come up with a new fraction that's equivalent to this one, but just doesn't have the radical in the denominator, by default that's a 2, right, since there's nothing written there. So this process is just telling you that what you need to do is multiply the numerator and denominator by root 3 over 3. And now when we multiply the denominators, that's just going to give me a 3. And then I'll have a root 3. So 1 over root 3 is equivalent to root 3 over 3. Right? Whereas the benefit of this one is that there's just no radical in the denominator. Okay? All right, so whenever we have something of this form, 1 over the even root of a, the square root of a, then the process is just going to be to multiply it by another radical root a, and it should work. Okay, but if we have something a little bit more complicated where it's not necessarily a square root, then what we want to do is multiply it by another root of the same index n, but we want a different exponent. I want a new exponent such that whenever I add those two, they add up to n. That's what we want, so that they reduce. So for example, if I had 1 over the 5th root of 2 squared, like that, it wouldn't make sense for me to just kind of copy this and say it's the 5th root of 2 squared over the 5th root of 2 squared. Because if I do that, then when I bring these two together, I'll just have 2 to the 4th power. And that does not simplify the way I want it to. Instead, what I want to do is I don't want to raise this guy to the power of 2 to match that. What I want to do is I want to raise it to a power such that they add up to the index. See, they'll add up to 5 now. If I multiply these two together now, I'll have the 5th root of 2 to the 3rd power over, and now I'll have the 5th root of 2 to the 2nd power times 2 to the 3rd power. They add up to 5, and now the denominator will just be a 2. And that's our goal, to get rid of the radical in the denominator. 2 to the 5th power inside the 5th root. The numerator stays the same, 2 to the 3rd power. So I'll end up root of 2 to the 3rd in the numerator. Good. So we say that 1 over the 5th root of 2 squared, which is a 4, is really equal to the 5th root of 2 to the 3rd, which is really an 8, all over 2. Right? That's what we want to be able to state. Good. And in case I confused you a little, that's because this guy's a 4, 2 to the 4, and that's where this guy comes in. And this guy is an 8. That's the 5th root of 8. Okay, so let's do a couple real quick examples here. Almost done. So if we want to rationalize this first one, we have 2 over root 3. That means that we have to multiply the numerator and denominator by root 3. And so that'll give us a 2 root 3 divided by 3. Good. Easy. For the second one, for b, we have 1 over for b, we have 1 over the cube root of 5. So that's 5 to the 1st power. So I need to multiply the numerator and denominator by the cube root of something. And there has to be a 5 in here. But I want to raise it to a power of something that such that these add up to that index of 3. So I have to put a 2 there, because the 1 plus the 2 will add up to 3. Okay. So this will end up being the cube root of 5 to the 1 plus 2 all over the cube root of 5 squared, which means that it's going to be equal to the cube root of 25, 5 squared is 25, divided by the cube root of 5 to the 3rd power, adding those two, which then reduces to 5. So my final answer will be the cube root of 25 divided by 5. Good. All right. Last one, C. We have the 7th root of 1 over a to the 2nd power. Well, we know that we can just separate this into the 7th root of 1 over the 7th root of a to the 2nd power. And the 7th root of 1, well, that's just going to be 1. So the initial statement just simplifies into having this, the 7th root of a to the 2nd power. And we just learned what we need to do here. So we got to multiply this by some version of the 7th root, and there's going to be an a there, but don't just copy a 2. The most common mistake is just to copy that denominator, but that's not going to work. They'll add up to 4 copies of a. We need 7 of them, right? So I need to put a 5 in here. Because a to the 2nd times a to the 5th adds up to a to the 7th, and then that'll be the thing that I need. So this will be a to the 5th, and now all of that will simplify to the 7th root of a to the 5th power will stay in the numerator. And in the denominator, I'll end up with the 7th root of a to the 2nd plus 5, which then gives me the 7th root of a to the 5th power divided by a. Right? We'll have a to the 7th, and the 7th root of a to the 7th is just going to be a, so that'll be our answer. Okay, so that should cover all the main ideas for this section. Let's look at the author's solutions. Same thing. A to the 5th, a to the 5th. Yep, here are the solutions from the author. Match up what we did. Okay, that should cover all the concepts for this section. Okay, so let me know if you have any questions.